Not every system of equations has a solution which is as simple as a specific value for x and a specific value for y. Sometimes, systems of equations may have no solution whatsoever. In other words, there are no values of x and y that satisfy both equations simultaneously. Or, at the other end of the spectrum, a system of equations may have infinitely many different solutions, infinitely many different values of x and y that solve both equations simultaneously. In this example, we'll attempt to solve this system of equations using a technique of our choice and discover what happens along the way in that solution if the solution of that system of equations is not as simple as just a single pair of numbers. So to solve this system of equations, we'll begin as though it were any other system and choose a technique for its solution. Here I'll choose the technique of elimination, singling out the y variable and realizing that if I multiply the first equation by -2, then the first equation will have a y term of -2y, the second equation has a y term of +2y, and when those equations are added together, we will eliminate the y variable. So I'll multiply the first equation by -2 to get -4x minus 2y equals -6. The second equation remains 4x plus 2y equals 6. And so to eliminate y, I can merely add the two equations together. But when we do that, something surprising happens. Not only is the y variable eliminated, because -2y is added to +2y, but the x variable is also eliminated at the same time by adding -4x to +4x. So both of the variables have disappeared in this process of elimination. And the equation that we're left with has no variables whatsoever. This is a big red flag. Anytime that all of your variables vanish in any kind of equation, it means that something fishy is going on. It means that your variables may not have the influence to determine whether that system of equations is solved or not that you would have expected them to have. So right away, we suspect that this system of equations will not have a straightforward solution. Now the question is, what manner of solution does it have? When all of the variables disappear from an equation, both sides of that equation become constants, just numbers. In this example, both sides of our equation are now the number 0. That's an example of an equation which is a true statement. 0 is in fact equal to 0, regardless of the values that x or y or any other variable happen to take. So when this happens, when our variables vanish and leave us with a true statement, it's an indicator that this system of equations has infinitely many solutions. The reason for this is that it's an indicator that actually both of our original equations are telling us the very same thing about the relationship between the variables x and y. And therefore, we don't have enough information to determine a unique value for those two variables. What we'll do in a situation like this is first of all report that there are infinitely many solutions to the system. But then second of all, we want to describe the nature of those infinitely many solutions, which we can do by describing the solution set as though it were a line in slope-intercept form in the xy plane. To do that, all we need to do is solve one of our original equations to get the y by itself, choosing the original equation 2x plus y equals 3 and subtracting 2x from both sides gives me a description of all infinitely many of my solutions. They are points on the line y equals 3 minus 2x. So when all of our variables disappear in our solution and leave us with a true equation, like 0 equals 0, our system of equations has infinitely many solutions, and solving one of the original equations for y will give us a description of those solutions as a line in slope-intercept form. This is not, however, the only possibility for what happens when all of our variables disappear. If we go back and change our original problem statement, I'm going to change the 6 in the original second equation into an 8. Making that change and following it through, we find out that when we add these two equations together for this system, and the y's cancel, and the x's also cancel simultaneously, just as before, the equation that we're now left with has a 0 on the left-hand side, but a 2 on the right-hand side. And so the equation that we have now is a false statement. 0 is not equal to 2, no matter what values x or y or any other variable may happen to take. Therefore, if there was a pair of numbers x and y that satisfy our original system of equations, then that would have to imply that 0 is equal to 2. Since 0 is not equal to 2, that implies that there is no value of x and y that solve our original system of equations, and we can merely report that our system has no solution, and stop right there. So anytime in the process of solving a system of equations that all of your variables vanish, you know that something funny is going on. If when the variables vanish you're left with a true equation like 0 equals 0, then your system had infinitely many solutions, and solving one of the original equations for y can describe that set of solutions as a line in slope-intercept format. On the other hand, if when the variables disappear, they leave behind a false equation, like 0 equals 2, then our original system of equations has no solution whatsoever, and we may report that fact and stop.